Hello everyone, I am Vatsal and I am from the Physics of Fluids group at University of Twente. I welcome you all to the online version of my APS-DFD talk on Taylor-Culick retractions. This work has been done with Datta Flose and two of our colleagues, Udalok Sen and Pallav Kant. Before I start, let me give you a real-life example of Taylor-Culick retractions. This is a soap bubble falling on a needle, and as it falls, a hole forms over here and then the bubble bursts. Of course, this process is governed by capillary forces. Once there is a hole, the only way to minimize surface energy is if the entire liquid sheet would vanish. Today we are going to talk about such retraction processes. As physicists, we often like to simplify the problem. So let us forget about the curvature of the previous soap bubble and talk about flat films that might retract once they are punctured. Particularly, let us look at this configuration where this black line is the axis of symmetry, and there's this water film that is retracting towards the right. And this is governed by the surface tension forces, especially the surface tension coefficient between film and air, is given by gamma FA. And another control parameter, one control parameter in this problem is the Onezov number of the film, which is nothing but the ratio of two time scales, that is the inertial capillary time scale and the inertial viscous time scale. In an ideal setting, such a retraction happens at a constant velocity, and that velocity is given by this Taylor-Culick velocity. In order to identify how this velocity comes up, let's look at a bit of a history of this problem. So if we approach this problem from a force balance perspective, then Taylor has a very nice article in 1959 where he balances the net surface tension force with the net rate of change of momentum. And here, if we assume that the velocity is constant, then the only thing that we need to figure out is the rate of change of mass, which can be done using continuity equation. And after some algebra, we can find this velocity over here. Now, of course, if we approach this problem from an energetics perspective, then Culick played a major role by identifying that the net surface energy released goes into increasing the kinetic energy of the film and the viscous dissipation inside the liquid film. And it turns out that both these terms have exactly the same form. And again, by some algebra, you would get this Taylor-Culick velocity, which is the same as over here. Now, of course, here I must mention that we assume that the film is infinite. That is, the length to thickness ratio of the film is much larger than the Onezov number. In order to study finite films, I recommend reading articles from John Louis Pearson's group, who have done a very nice job on this particular problem. Now, just to close the historical part, let us look at a representative simulation. Throughout this talk, I will show such videos where on the left-hand side, I show the velocity field normalized with the Taylor-Culick velocity, and on the right-hand side, I show the rate of viscous dissipation normalized with a maximum rate at any instant on a log 10 scale. We do this in order to identify regions with highest viscous dissipation. As you saw, the tip very quickly reaches the Taylor-Culick velocity, which is 1 over here. And of course, we can also notice that the dissipation is highest in the neck regions over there. And now let us look at the energies. The net surface energy released goes into the kinetic energy of the film and viscous dissipation. And it helps to look at, instead of energies, it helps to look at the rates of such energies because of the infinite film. And what you can notice over here is that half of this energy goes into the increase in kinetic energy of the film, and the remaining goes into the viscous dissipation. So what we have done is that we were able to reproduce both Taylor's as well as Culick's calculation. But I promise that I will talk about something different today. So let us look at a different canonical configuration, namely one where the surrounding is filled with a viscous oil. And luckily, there is already a paper in literature where David Curry et al. Looks at such a configuration where they essentially look at the retraction of water films inside oil baths. For such a system, there are two control parameters. One is the Onezov number based on the film viscosity, and another is the Onezov number based on the surrounding medium viscosity. Now, first we look at a case where Onezov number of the surrounding is very small, which is this case over here. Just note that on the left hand side now, I normalize with the final tip velocity, which is Vf. So what we see is that similar to the classical Taylor-Culick case, the tip quickly reaches this constant velocity. However, unlike classical case, we must remember that now it's not just the film that moves, but it also moves along with the surrounding bulk, and the surrounding bulk also has inertia. And it so happens that that would also take away some of the energy that is released. And this is often referred to as the added mass effect. What we can do is we can define a Weber number based on the film velocity, and look at how this velocity changes. Now, it turns out that for low OHS numbers, the velocity is still a constant, but the magnitude is smaller than the Taylor-Culick velocity. Remember, if the Taylor-Culick velocity has a Weber number of film, which is 1. So this is the classical Taylor-Culick. However, this particular case, where you have the added mass from the surrounding medium, the velocities are smaller than the classical case. Now, what happens if we increase the surrounding Onezov number? So let us look at one case over here where the surrounding Onezov number is 1. And what we see is that tip still reaches a constant velocity, but the viscous dissipation is much higher in the surrounding as compared to the film. And increasing the Resolve number in the surrounding even further. So here the Resolve number of the surrounding is 100. We notice that the entirety of dissipation happens outside the film, as is evident by these black regions at the tip. And to summarize, here are the three cases that you just saw. As we move down, the unresolved number of the surrounding increases, and basically there is this first case where the velocities are comparable to the Taylor-Culick velocity, whereas in these two cases the velocity decreases a lot, which you can notice by noticing that. The tip reaches the same spatial location, but the times that it takes for the tip to reach there are much larger. So what we can do is now let us go back to the plot, and we try to plot these velocities on this Weber and on this solid space. And what we can see is a graph that looks like this. And of course, there is one regime, which is the inertial regime, where these velocities are constant. And then there is this second regime where velocity decreases with increasing unresolved number. If we plot the data points from the Vidkare et al. Paper, we can see that these data points match quite nicely with our numerical results. And of course, we can identify a scaling law over here, which essentially says that Weber number goes as 1 over unresolved surrounding squared. Now, the idea would be, can we understand this scaling law? And for that, let us look at the dynamics of this problem. And here we are going to balance the capillary retraction force with the viscous resistance that comes from the surrounding. So basically, F gamma, we can balance it with F eta. F gamma is easy as it is same as the previous case. For F eta, we have to look into Stokes flow or Rossini approximation. And in both these flows, which is essentially flow of an object through a viscous medium, we know that the forces in the first approximation, it scales with viscosity of the surrounding times the velocity of motion. And if we now look at this balance over here, we can do one of two things. We can either divide both sides with the Taylor-Culick velocity, and then we recover the scaling law that we saw in the previous slide. Or what we can also do is we can rearrange these terms in order to define another dimensionless number, which is the capillary number based on the surrounding viscosity, and this basically gives you that this capillary number should be constant. Now, what we can do is we can either plot a capillary number versus unresolved number, or we can plot the Weber number versus unresolved number. And essentially, in the initial limit, the Weber number based on the film velocity is constant, whereas in the viscous limit, the capillary number based on the surrounding viscosity is constant. And of course, one thing that I did not mention before is that all these things are independent of the unresolved number of the film, which is also the case for classical Taylor-Culick retractions. Now let us probe the energies associated with this process. And here the red symbols show the total viscous dissipation, and the purple data points show the rate of change of kinetic energy. In the inertial limit, all the surface energy goes into the kinetic energy as well as viscous dissipation, and that aligns perfectly with Culick's arguments over here. Whereas if we look at the viscous limit, the entire surface energy goes into viscous dissipation, and as is very clear from this data point over here. And in fact, what happens is that this viscous dissipation is concentrated entirely in the surrounding bulk, which is evident if we also plot the viscous dissipation inside the liquid film, and we see that the dissipation inside the film as well as the kinetic energy of the film, both of them decreases, whereas the viscous dissipation in the bulk, it increases, and it saturates to be equal to the net surface energy released in the process. That brings me to the conclusion of my talk. We studied two canonical configurations in this work. First, the classical Taylor-Culick, where the film Weber number remains constant, and second, the two-phase Taylor-Culick, where the surrounding viscous dissipation plays a role, and there we have two regimes. One is the inertial regime, which is similar to the classical Taylor-Culick, where film Weber number is a constant, and second is the viscous regime, where the surrounding capillary number is a constant. But the story is not over yet. One can obviously ask what happens when the half of the surrounding is viscous oil and the other half is air. We call this configuration a three-phase Taylor-Culick retraction, where water film is sandwiched between two media. And for part of our work, I urge you to listen to Udalok's presentation, which should be the next video if you are watching it online. And for now, all I can say is that the three-phase Taylor-Culick is still an open question, where many interesting things would happen as well. And with that, I am at my final slide. A special shout out to the open source free software program Viscous, where all these simulations are done. We believe in openness and science, and therefore, in that spirit, all the codes that are used in this talk will soon be up on GitHub and Basilisk Sandbox. Thank you for your attention. please feel free to reach out to me if you are watching this online, or find me during APS if you will attend it offline. Thank you so much.